Okay, so it's good to see everybody. The homework issue, as you probably saw in the announcement, is still yet to be resolved. Yeah, Pearson really sucks is the moral of the story, but we'll get it done eventually. And if by Monday, for whatever reason, it's not resolved with Pearson, then I'll just start making my own homeworks. So you'll have homework either way. It's just a question of how convenient it will be. But do check on the announcements that I posted a couple, including saying that if you go to the Pages tab on Canvas, that's where I'm going to be posting the links to the lecture recordings, just because that way I can edit it more easily. And Canvas only has 2 gigs of storage per site, so I can't add MP4s or it would just use it all up immediately. So anyways, cloud recording links should be good. I do have office hours today after class. So basically right after class, I'm just gonna start walking towards my office with whoever wants to come. And we can talk about any of the physics or any admin questions that you might have. And there will be a quiz this week. So the homework is kind of messed up, but there will still be a quiz tomorrow that you can take anytime after discussion ends all the way until like midnight. And so just find 20-30 minutes to take that at some point in your day. It'll be a so I just made the question. It's kind of a mix of a lot of the topics we've been doing in a semi-cohesive way. But you will have some component due to hydrostatic pressure, something due to surface tension, and like just looking at pressure in general, maybe some stuff about density as well. So it's all kind of comes together, which is how real physics problems work. But I've tested it out with some people, so it should be doable in 15-20 minutes, and you'll have 30. So anyways, hopefully that works out. And I'll give you some formulas with the quiz, but please don't use any other like external resources while you're taking it, and you should take the quizzes by yourself. You can have a calculator, of course. You'll almost certainly want one. Anyways, so I'll have time for questions after class during office hours, but today I want to jump into pick back up where we left off. Oh, I also wanted to say, starting tomorrow, we're going to have lecture demos. So got that organized with the department. And we've got some cool ones for you coming up on, atmospheric pressure. We've got some capillary action stuff, and we've got some fluid flow things that we're going to cover today. So hopefully that'll be fun. Anyways, so let's hop right in. So where we left off was looking at surface tension. And specifically, the last thing we did was look at these spheres where we found that the difference in pressure between the inside and the outside for a solid sphere is something like 2 gamma over r. Whereas for, so this is for sort of a filled bubble. So it could be an air bubble in water, or it could be a water bubble in air, or a honey bubble in oil. The possibilities are endless, but just one surface. And that if we have 2 surfaces, so something like a soap bubble, I'm just going to put soap bubble here since that's the most common example, then we have an extra factor of 2, which is basically entirely due to the fact that there's an inner surface where there's air inside touching the soapy water, and there's an outer surface where there's air outside touching the soapy water. And both of those cause some layer of molecules to be unhappy. Molecules don't like to be on the surface, and so they exert a surface tension, basically trying to escape that unfortunate location for themselves. And the pressure that we see here, so the difference in pressure between the outside and the inside, it scales with surface tension. So something like water with a really high surface tension will tend to have a higher pressure inside bubbles. And this is actually why soap bubbles, we have to add soap. So soap is an example of a surfactant. A surfactant is just a material that decreases gamma, like decreases the surface tension. And so by adding that soap, we are able to form bubbles that are large enough to be fun for children to play with and such. So if you just tried to form a soap bubble out of pure water, that gamma, that surface tension is so strong that it won't let you easily, make these bubbles. It won't be stable. And so the weird thing about this formula, though, is that as the bubbles get smaller and smaller, the pressure inside in comparison to the outside gets bigger, which is really weird. And so this is a really common question that you may see again in the future, which is if you have this situation here, does air flow this way or does air flow this way? So who thinks that the bigger bubble would inflate the smaller bubble? Who thinks the smaller bubble would inflate the bigger bubble? Okay, good. So I think that's what we want to have here. And the idea is that the smaller bubble has a smaller radius. So when we use this formula that the change in pressure or the difference in the pressure is the inversely proportional to the radius, that smaller bubble has a lot more pressure. So that air is going to be pushed out into the bigger bubble. And we sort of mentioned this right at the end of yesterday, but this creates a problem for the lungs because the lungs are a bunch of bubbles. So the alveoli are little sacs of air covered in cells, but they're still effectively like these small bubbles. And so if one alveolus started to grow bigger, it would naturally suck the air from all the other ones and completely wreck your lungs because your lungs really require there being an insane number of tiny bubbles so that the surface area is really high, so that the gas exchange between CO2 and oxygen can happen during the course of one breath cycle. And so again, as with a lot of these situations with surface tension, the way you fix this is by having a surfactant, right? So surfactant just means you have a lower gamma, just to write that down somewhere. And the thing about surfactants, though, is that they're some solute, right? You're dissolving some substance into this liquid, or you can also do them in gaseous states, but it's really tricky. Generally, liquids are things that have surfactants. And so as those lung alveoli expand, there's more and more area. And so the surfactant concentration decreases. So as the alveoli expand, we have less surfactant, so the surface tension actually gets bigger. Okay, so that causes the delta P to get bigger. And that allows the air to be pushed out of these larger sacs back into the smaller ones, because the smaller ones have a lot of surfactant concentration. And so I'm not going to develop the formulas for that here. That's generally something that you would talk about in a more advanced chemistry class, because we start thinking about concentrations. That's not in my pay grade. But it's just something to be aware of, this explanation that when you start to add some solution of surfactant, then you can have larger bubbles with a smaller surface tension and therefore have pressure equilibrium occur more naturally. Okay. So now moving on, this is the idea of contact angles that we mentioned a little bit yesterday. And if you saw my announcement, I said something a little bit wrong, so I wanted to correct that. So when we were thinking about this needle problem, just to go back to it, if the needle is really light and barely weighing on the surface of the water, then this angle phi on either side would be what we call the contact angle, which is basically, even if there are no forces involved, like due to gravity or pushing or pulling or such, liquids touching a solid will tend to be pulled by what we call adhesive forces, so molecular forces between the solid and the liquid. such that they form some consistent contact angle. Now those angles are tricky, as we'll talk about in a moment, because they depend on how clean the surface is and how rough it is and that sort of thing. But in this problem, when we start to add a lot of mass to the system, the water actually will envelop around the needle. And so since we're trying to find the maximum mass in this problem, what I should have said is that phi is going to go to 90 degrees. And so the sine of phi term just goes to 1. So we can kind of ignore the effect of the angle here. And we would just say that mg is balanced by 2 gamma L. And so m is just 2 gamma L over g. So I apologize for that error yesterday. If we were working with a very light needle, then we would use the actual contact angle. So just to go back here, we can start to see what I mean by contact angle with some of these images. So if something has a smaller than 90-degree contact angle, what we say is that that surface is, in the case of water, hydrophilic. So it attracts the water. It wants it to spread out. Whereas if something has a larger than 90-degree surface angle, contact angle, as you can see over here, we call that kind of surface hydrophobic in the case of water contact angles. So it'll tend to cause the fluid to bead up. And the reason for that is that the water is more strongly attracted to itself than it is to that material. Okay, so we call internal forces in a fluid cohesive, and we call external forces adhesive. And so when you're working with surface tension, and especially with things like contact angles or capillary action, an important question to ask yourself, or something to be aware of, is what is the balance between adhesive and cohesive forces? So, for example, water in a test tube, the adhesive forces are stronger. So water is actually more strongly attracted to the glass of a test tube than it is to itself, which is kind of crazy because water really likes itself. So that's telling you something about the strength of the adhesive forces. Meanwhile, mercury, which actually has an even larger surface tension than water, mercury has one of the largest known surface tensions of any fluid. It is more strongly attracted to itself. So it'll tend to kind of bubble up. And that's why the meniscus seen if you put mercury in a test tube, which we should have for you tomorrow, some mercury to look at, is actually an upward convex meniscus. And so this table lists some common contact angles. You'll always be given them. I think there was a question yesterday that was very good, which is, is there any way to calculate these contact angles? And the answer is not any easy way. You have to do some numerical simulation. It's very tricky. And these are only rough values because, like I said, if there are any surface disruptions, then the contact angle can dramatically change. Okay, so any questions about contact angles while we're here? Good. Okay, so this gets us into what's known as capillary action. So a capillary tube is just a tube that has a really small diameter relative to the surface tension strength of a fluid. Okay, so if you have a very large surface tension fluid, then it can exhibit capillary action on larger scales. But generally, capillary tubes are going to be really tiny, like millimeter scale and smaller. And so what happens is that as you put fluid, so you put some fluid beneath a very small tube, and the adhesive forces between the fluid and the tube want to pull the fluid up the tube. And so those forces have some strength that's based on the surface tension, right? It's going to be gamma times some sort of length, contact length. And we'll derive this in a second, but basically that upward force is balanced by the fact that as we pull fluid up the tube, that column of liquid has a weight. So there's going to be an mg pulling down. And so the fluid will just keep moving up the tube, up the tube, up the tube, until the upward force due to the surface tension is equal to the downward force due to the weight of the fluid that we've pulled above the surface. Okay, so to show you what this looks like mathematically, so we can imagine this part of the fluid above the surface of the water as some box for free body diagram purposes. And so we have a surface tension pointing upward. We have a weight pointing downward. Okay, the weight is pretty easy. So this is just going to be rho times V times G, right? The mass for fluids, we tend to like to write this as a density times a volume, and then G stays the same. And then if we're in a cylindrical tube, like with a circular cross section, then this volume is just pi r squared times h. So this is mg. So that's just the volume of a cylinder. And the reason we want to write it this way is because we're interested in how far up the tube the fluid's going. So we want to get that h in there somehow. Now, the tension force, the surface tension, we know it's going to be something like gamma L. That's just kind of the definition of gamma. And so what is the length scale that's relevant? And remember, this is about a surface, right? Surface tension is something that occurs on the boundary between the liquid and the gas. So does anyone have any guesses about what should L be here? This is often the hardest part of these problems, is figuring out L. I think I see some people mouthing it. So it's 2 pi r. Okay, so if you think of the top of the column, there's liquid on the top, and that's where the surface is, right? The surface of the liquid is on top of the column. And in the cylindrical tube, we have this 2 pi r, the circumference of the tube, which is where the liquid, the gas, and the glass of the tube, or whatever it's made of, are all touching each other. Okay, so that's the length that we want to use when we're thinking about the strength of the surface tension. Okay, and then we also have to consider, excuse me, the fact that we have some contact angle here, right? So water forms a meniscus in a tube, as you've probably all seen in chemistry class. And so this angle here, this is the contact angle. And we can see, so surface tension can only pull along a surface. This is a really important principle that I don't think I emphasized enough yesterday. So surface tension is something, so remember the experiment where we have a rectangle and we were pulling that wire. The surface tension is trying to pull the wire back into the rectangle. And so if you imagine a surface, it can only exhibit forces that are parallel to it. It has no mechanism by which it can exert perpendicular forces. So this is all to say that we should slap a cosine theta in here, because this component, which is the cosine theta component, is the only one in the vertical direction that's capable of lifting the fluid. The other component just serves to form this meniscus shape and hold the fluid in this kind of bowl at the top. And so putting this all together, this is gamma 2 pi r cosine theta. And then we just equate these two. So to find the maximum height that a capillary tube can pull a fluid, we say, I'll go to this side, that rho pi r squared h times g equals gamma 2 pi r times cosine theta. And so the pi's are going to cancel. One of the r's is going to cancel. And now we can solve for the height. So we're just going to divide by rho rg. We get 2 gamma cosine theta over rho r g. So this is our formula to find the height of a capillary tube, and we can do some checks to make sure this makes sense. So the first thing we check is that there's a gamma in there. That's good. That means that the more surface tension a fluid has, the more height it will be pulled through a capillary tube. The second thing we check is that there's a cosine theta in there. That's really important because that's telling you about the adhesion. So the force between the fluid and the glass of the tube, for example, right? So if we want this height to be really large, we need cosine theta to be close to 1. We just, because cosine can only be between 1 and -1. And so for water, remember for water with clean glass, the contact angle is almost 0. That's telling you that the adhesive forces are very strong. The water is really being pulled by the glass. And so in that case, the height of a capillary tube of water and glass is basically just 2 gamma over rho rg. The cosine theta becomes 1, so we can ignore it. For something like mercury on glass, you can see the contact angle is 130. So something really weird happens. And again, we're going to see it happen in the class tomorrow, which is that mercury, the cosine theta is negative, right? The cosine of an angle that's between 90 and 180 is negative. And so mercury actually sinks below the surface in a capillary tube. So that negative, you can just interpret it as below the surface. And the height will tell you how far below the surface it moves. So it's a really weird effect caused by the fact that mercury is actually like repelled in a way by the surface. It's much more strongly attracted to itself. And then the rho rg is just telling you that it's harder to lift a heavier fluid, and it's also harder to lift a fluid in a bigger tube, and it's also harder to lift a fluid on a bigger planet, or one with a larger g. So hopefully this formula, the location of all the terms makes sense once you walk through it. The 2, that's what gets you if you don't have access to a formula sheet or remember it. But it's not too important in terms of how to compare different tubes exhibiting capillary action. Okay, so I put a big picture of a tree here, and this is something that's kind of there's like a Dunning-Kruger effect with understanding how trees work, which it turns out is really hard. So as we learned on Monday, the height that a water barometer will lift to under 1 atmosphere of pressure is about 10 meters. So if I'm a tree and I am trying to get water from the ground and I think of myself as like sucking on a straw, I could only grow 10 meters tall. 33 feet tall. Because if I grew any higher than that, no matter how hard I suck on the straw, no water will be able to rise higher than 10 meters. I'll just create a vacuum above that top of the column of water. So it'll just be a barometer with a vacuum on top. And so this is really weird because we know that some trees, like if you go up to Northern California, the redwoods are much, much taller than that. So trees can be 100 meters tall, which is really crazy. So how do they get their water? Well, if we plug in the radius for the xylem, which is the tubes in a tree that transmit fluid, we would actually find that, and you'll have to do this yourself at some point, we'll find that the height that capillary action can lift water in a tree is only a few meters. It's actually less than the height of the barometer, a water barometer. So capillary action is not the real answer here in terms of how, so capillary action is very useful for small plants. Like if you plant a little basil plant or something, it loves capillary action. That's how it gets all its water. But if you plant a big redwood tree, it has to have some other trick. And it turns out what it does is that it has leaves that are constantly evaporating water. And you might say, hold on a second, isn't that just like suction? So it would only be able to lift water 10 meters. But it's actually different. It's related to our next topic, which is fluid flow. So the fluid is flowing through the tree, out through the leaves, And because water has such a strong surface tension, it can actually pull the column of water, which is really weird. So this is one of the only places where this happens. Usually you can only push on a fluid, right? If I push on a balloon, I can compress it, but I can't like pull on the fluid usually. It just wouldn't follow me. It would ignore what I was doing. But with water, under very special conditions, like you find in these large trees with small tubes, you can pull on the water. So it's almost like a rope of water. And there's so much evaporation in a tree, like many liters per minute. So these big trees really require a lot of water, very moist conditions, which is why they're not found everywhere. Then you can pull the water up the tree all 100 meters and, live a happy life. The problem with this is that if even a single a single air bubble gets into that tube, the whole thing fails, right? So if you imagine one of these trees, they have these long tubes and the water is filling the tube and it's being pulled up by these surface tension forces due to the evaporation in the leaves. If a single little air bubble gets in there, then the surface tension that force can't be transmitted. So the tube will collapse. Trees are very clever and they're good at not having this happen. But something that they can't control is that during winter, water freezes. And so during that freeze thaw process, you'll often get air bubbles forming. And this is actually, it's really cool. This is the explanation for tree rings. So what the tree does is every year it grows an entire new set of tubes, an entire new xylem, which is the outermost ring of the tree. And so by understanding some surface tension physics, we can understand why trees have rings, which is kind of cool. Okay, so any questions about this stuff? Good. So we'll do one quick problem. So we have a capillary tube used to sample some blood. So this is a common method to draw small samples of blood, especially like from infants and things like that. So it has an inner diameter of 0.8 millimeters. So the diameter is 0.8 millimeters. To what height will the blood rise in a vertical capillary tube? Okay, so this is just basically applying the formula. So from the last slide, the height is 2 gamma cosine theta over rho rg. And so we can go back to our table. If you're doing homework, once it finally is working, you'll often have to consult your electronic textbook or whatever format to look at the tables of values in order to answer these problems. On a quiz or a final, we'll just give you the numbers you need, so don't worry about it too much. So the gamma for blood is 52 millinewtons per meter. So that's 0.052 newtons per meter. The wetting angle for blood is about the same as that for water. It's about 25 degrees with glass. And then the density of blood is just a little bit more than water. It's 1060 kilograms per cubic meter. They tell us the diameter of the tube, so we want to convert that to a radius, so just 4 times 10 to the minus 4 meters, right? We want to convert from millimeters. And then G is 9.8 meters per second squared. Okay, so we can plug all of this into our calculator. And the height that we get is 23 times 10 to the minus 3 meters, or 23 millimeters. Okay, and so common medical capillary tubes are actually longer than this. I mean, you obviously want a little bit of gap so the blood doesn't just spurt out the end, but if you hold them horizontally, then you can fill a longer tube, because then only, and this is a problem that we might give you at some point, if you hold a capillary tube like this, then this is the relevant height in terms of the capillary action. And so it can fill a longer tube, but the amount of vertical distance the fluid travels would be the same. And so, yeah, this is what a capillary action problem might look like. They're usually pretty straightforward, but you might be asked to like compare the height of different radii or compare the height for different fluids. So there are lots of permutations of these problems, but they all kind of come back to this formula. Okay. Does that problem feel pretty straightforward? Good. Okay, so we'll move on to the next topic then, which is fluid flow. And this is going to finish us off. We're going to do ideal fluid flow and then viscous fluid flow, and that'll basically finish off chapter 9. So we're getting through it. So anyways, you probably all have experienced fluid flowing in a lot of different ways. So whether that's the current in an ocean or the wind flowing around your body, like it's flowing around this car. And we're going to get into the details of this a little bit later, but I just wanted to mention here that there are 2 types of fluid flow. So we're going to really dig into this, but there is laminar flow, which is where the fluid is kind of nice, and you can imagine different parts of the fluid are not crossing each other. They're just flowing in pretty straight lines. Maybe those lines curve, but there's always some gap between each fluid flow line. And this is in comparison to turbulent flow, which is much more complex to model, but it's a very common phenomenon, especially with gases. And that's where you just get a bunch of craziness, right? The fluid spins over itself, creates little vortices and whirls and everything else. It's really quite beautiful. And it turns out there's a nice diagnostic, like a nice equation we can use to figure out which type of flow is happening in a fluid in a given system. And it's called the Reynolds number. So we'll get to that pretty soon. But for now, we should talk about fluid flow rate and what's known as the continuity equation. So when we have a fluid, we define something called Q, which is the flow rate. And more precisely, it's the volume or the volumetric flow rate. And so this is the change in volume per change in time for a fluid relative to some point, right? So you can imagine if you have a garden hose, the water's flowing through it. And if you look at some, like maybe the end of the hose where the water's coming out, you could ask how many liters of fluid are leaving the garden hose every second. That would be a volumetric flow rate. And the important idea in regard to volumetric flow rate is that for a liquid, which is generally going to be incompressible. So in a liquid, we can't, if we squeeze it, it's not going to occupy a smaller space. The density will stay the same. It's another way of saying this. For an incompressible fluid, we can write what's known as the continuity equation, which is just that the flow rate at one point in a tube is the same as the flow rate at another place in a tube. So how much water is coming out of your garden hose? Well, it's the same amount of water as is coming into your garden hose. And this sounds kind of basic, and we can do this bottom right problem here pretty easily just with this idea, right? So we just need to figure out how much fluid is flowing into this system. So Q in here is 10 plus 2 plus 1, whereas Q out is 8 plus 4 plus X. And so we can see that X is what here? Just 1, exactly. And it's a flow outward. So you can do really simple problems like this where you're just kind of thinking about equating the flow into a system to the flow out of a system. Nothing tricky there. But fluid flow gets really interesting when you realize that volume per time, this is like a cubic meters per second, let's say. So this is the same as if we had a velocity times an area, right? A velocity times an area is also cubic meters per second. And so it turns out that this is an equivalent way of talking about fluid flow rate, is to say, how big is your pipe and how fast is the fluid flowing through it? We multiply these two numbers and we find out how much fluid is flowing through the pipe per second. Okay, and I'm saying pipe here, but you can do this even with systems that are open to the environment, as long as the flow is laminar, right? If it's laminar, those lines are sticking together. They're not bunching up and being weird. So we can still apply these continuity relationships in those cases. Okay, so we can just rewrite this then as V naught A naught equals VF AF. And this tells us something really nice, which is known as the Venturi effect, which is that if we decrease the area of a pipe, we increase the velocity of the fluid. And the reason for that is that sort of the fluid behind it, it gets bunched up. And so it starts pushing harder and harder, and it accelerates that fluid in the smaller section to a larger velocity. Okay, so if you have a closed system, or a system exhibiting laminar flow, then a restriction causes fluid to flow faster. You can feel this with your hands. If you take your hands and kind of blow between them and then put them closer and closer together, and you'll really feel the fluid flowing most quickly as your hands get very close together. And this works as long as your breath is pretty laminar, which will typically be the case. But anyways, so it has a lot of important implications, but it's most useful in combination with some other tools that we're about to develop. Okay, but how does the continuity equation feel to people? Pretty good. Okay, so the smaller the area of the cross-sectional area of the pipe, the faster the fluid's going to flow. That's the important relationship. Okay. So I've got this picture here to remind me to talk about Bernoulli, who was really a pioneer in all things fluid flow. And he came up with a really clever relationship to describe how different properties of a flowing fluid are related. And so it's known as Bernoulli's equation. And notably, we have the pressure plus 1/2 rho V squared. And then we can even add rho GH is conserved. So whatever this is, at some point, it'll be the same thing at a different point in the fluid. And if you paid attention in 3A, this equation should probably look pretty familiar, right? What does this look like? We have a 1/2 V squared. We have a GH. So this is basically an expression of energy conservation, right? It's very similar to work. So the pressure is like a work. So work plus 1/2 mv squared, that 1/2 rho v squared is like a kinetic energy. And then the rho gh is like a gravitational energy, a potential energy. And so Bernoulli's equation, it's basically just saying that the energy in a fluid is conserved. We don't have to worry about it just disappearing magically. Now, for the moment, let's ignore these height components. So if fluid is flowing in a horizontal pipe, then we don't have to worry about the height changing. So for horizontal pipes, And so in this case, Bernoulli's equation tells us something really interesting. So if the fluid is flowing faster in one location relative to another, and they're both at the same height, what happens to the pressure? Exactly, it's going to decrease. So the faster the fluid's flowing, if this term gets bigger, this term has to get smaller if they're going to, if the sum of them is going to remain constant. Okay, so this is a really, really critical result in ideal fluid flow. So we're not thinking about fluids having viscosity at the moment. So just something like air or even water is a pretty good example of this. As the fluid flows faster and faster through some container, which often means as it flows through a constricted region, right, the pressure is going to drop. And so one of the most important examples of this is in airplane wings. You often hear maybe in like elementary school science classes or middle school science classes, if you're like, why does a plane fly? And your teacher will just say something like, it's Bernoulli's equation. You'll learn about it eventually. Well, now is eventually. And so the idea is that with a wing, you choose a geometry, you choose a shape of a wing such that air is deflected. And there are a lot of misconceptions about how wings work because the details are actually really tricky. But effectively, you're deflecting the air in such a way that the region above the wing has a lower pressure or a higher velocity, and the region below the wing has a higher pressure or a lower velocity. Now, it's not so simple as to say, you'll often hear people say, well, the air kind of traces around the wing and air molecules like to meet up at the end. It's not really true. The reality is just that the shape of the wing is deflecting air. And, this is pretty close to laminar flow, so that air is going to follow these nice clean lines. And in this deflection, you build up air at the bottom. That increases the pressure. If you imagine like moving your hand through the air, you're increasing the pressure on your palm, and that simultaneously just decreases the velocity from Bernoulli's equation. And it's a self-reinforcing effect. So if the velocity decreases, then you're increasing the pressure and so on. So it's not just a one-way street. It works both ways. If you change the velocity, you'll change the pressure. If you change the pressure, you'll change the velocity. It's just energy conservation. But the net result is that you have low pressure above the wing, high pressure below the wing. So you get lift, you feel pushed up. And this is a really marvelous fact. And it lets us move upward in a fluid, air, even though the buoyant force in air, right, is obviously incredibly small, unless you're a helium balloon or something. Okay. So now we can do a more thorough problem, but before we start this, let's actually have our couple-minute break. So a couple minutes to stretch and talk and get ready to do some more physics. Um, okay, so hopefully that was a good opportunity to, get back your brain from the fog. But we should probably hop into this next problem where we're gonna use both of the last two tools, right? Continuity and Bernoulli's equation to understand how the fluid's flowing here. And it's also a great problem because it throws in some gauge pressure stuff. So it'll be good to revisit that, although it's actually not very important here. Okay, so we have this pipe, 12 millimeter diameter. So that's pretty small, but it's still considered a large pipe relative to water's viscosity. So water has a very small viscosity, so it'll behave as an ideal fluid unless you're talking about sub-millimeter sized pipes. So very, very small things. But of course, the body has tons of sub-millimeter sized pipes, so we will have to pay attention to the viscosity eventually. But anyway, so we have this pipe and the water's flowing through it at a very respectable 4 meters per second. And it has a gauge pressure of 150 kilopascals. Remember, this is a very good number to know that 1 atmosphere is 100 kilopascals. So we could just as well say that the pressure in this larger region the gauge pressure is 1.5 atmospheres. And then this is where it's important to remember the definition of gauge pressure. So gauge pressure is what a pressure sensor that we built on Earth would tell you is the pressure inside here. And so the absolute pressure, you have to add 1 atmosphere to get that. So if we want the actual pressure here, it's 2.5 atmosphere, or 250,000 pascals. I just like using atmospheres because I think it gives you like a better feeling for it. But as we'll see, so Bernoulli's equation is P naught plus 1/2 rho V naught squared equals PF plus 1/2 rho VF squared. So this is a horizontal pipe, so we don't need the rho GH component to it again. But what I want you to see is that if we replace this with the gauge pressure initially plus 1 atmosphere, and we replace this P final with the gauge pressure final plus 1 atmosphere, that we can, because the pressure only appears as like an extra added term, we can just cancel the 1 atmosphere from both sides. So all of this is to say that for Bernoulli's equation, we don't actually need to care whether a pressure is a gauge pressure or an absolute pressure. And that's because of the specific form of the equation. However, when you get to the ideal gas law, which we will probably next week, we do have to always convert gauge pressures to absolute pressures, because the ideal gas law is a multiplicative equation. We're doing P times V equals nRT. So if we're trying to calculate some value, that plus 1 atmosphere doesn't nicely cancel. It gets all mixed into things because we're like distributing binomials. And so be careful with this. But for this problem, we don't have to think very hard about it, luckily. Okay, so to start then, we're trying to find the pressure in the small section of the pipe, but there's not an equation that will directly give that to us, because if we look at the Bernoulli's equation, we know the initial pressure and the initial velocity. We want to find the final velocity. We don't know it, but we also don't know the final pressure. We want to know the final pressure, but we also don't know the final velocity. So we have 2 things we don't know. And so in order to get this, we have to first find this final velocity. And we can do that with the continuity equation. So in ideal fluid flow problems, so things without viscosity, you'll often have to use both the continuity equation and Bernoulli's equation together, because they each tell you something slightly different about how the fluid changes as it passes through some smaller or bigger opening. Okay, so here we want to solve for V final. So we have A initial, V initial over A final, and they tell us all of these things, luckily. So remember that the area of a circle is either pi r squared, or we can just say pi d squared over 4 if we'd like. And so the pi and the over 4 are going to cancel. So we just have d initial squared times v initial over d final squared. Those are the diameters of the pipe. And so since they're both in units of millimeters, we actually don't need to convert them either. So we could just do 12 squared times 4 meters per second over 8 squared. And we get our velocity in the smaller section. So I'm getting 9 meters per second. And I plug that in. And now we can go to Bernoulli's equation. So I'm going to erase these little notes I made underneath here. And they tell us the pressure initially, and like we said, we can just use the gauge pressure here, since it's Bernoulli's equation just has pressure as an extra added term, plus 1/2 the rho for water is 1,000 kilograms per cubic meter. Well, we'll tell you that, but it's a good number to know. This is 4 squared, 4 meters per second squared, equals P final, which is what we'd like, plus 1/2, and then 1,009 squared. Okay, so now we just have to subtract this rightmost term from both sides to get P final on its own. And we get 120 kilopascals. And this is our gauge pressure, since we're calculating in Bernoulli's equation using a gauge pressure. I know I'm probably saying too much about the gauge pressure stuff, but please do be careful about it. And if you're ever in doubt, just convert it to an absolute pressure. That'll always work. But it is a handy shortcut to not have to do that with Bernoulli's equation. But anyways, so we see what we expected, right? We're going faster in the smaller region of pipe. So the area is smaller. So in order for the fluid to flow, it has to move faster through that region. And as it moves faster, some of its energy is going into motion, kinetic energy. So it has less energy to exert pressure. Okay, so it has a smaller pressure in that region. Yes.
Do we have to convert since it's a 12 millimeter diameter, how come we don't convert it into meters?
Yeah, so if you're ever in doubt, just convert it to meters. But here what's happening is we have a D naught on top, which is going to be in cubic millimeters, and we have a DF on bottom, which is going to be in cubic millimeters. And so those are just going to cancel. Whenever you have these proportionality relations, like XY initial equals XY final, you can just, if the X initial and X final are in the same units and you're not trying to solve for it, you can just leave them alone and they'll cancel.
And the A is area, right?
The A is area here, yes.
And then the pi's cancel out.
Exactly. So both of the areas will have a pi over 4 attached to them, right? So the pi d squared over 4. And so the pi over 4s are just going to cancel. And so that's why we can go from this A naught to this D naught here. Right. So let me write that out because I think it's maybe confusing. So we have A naught over AF times V naught. So A naught is pi D naught squared over 4 times V naught. And AF is pi DF squared over 4. And so we see that there's a pi on the top and the bottom, those are going to cancel. And there's a pi on the bottom and the top, so those are going to cancel. You remember your keep it, change it, rearrange it, divide by fraction rules. And so we're just left with a D naught squared, V naught over DF squared.
Yeah, the area was a higher square. How come we're using that diameter?
You don't have to use diameter, but it's just easier in this problem. So you could convert those, if you're uncomfortable with these steps, just convert the diameters into radii, and you can convert those into meters as well. And then do pi r squared for A naught, get a number, do pi r squared for AF, get a number, and just divide those two, and that'll work. There's no problem with that. It's just I'm lazy, as most physicists are, and so try to do as few steps as possible. So thank you. And if I do this in the future where something's confusing, definitely ask, and I'm happy to walk through it. Okay, any other questions on this example? So this is a type of problem that you'll definitely see in the future. So very good to know how to do it, but you can also rewatch the recordings if you forget. So no real loss here. Okay. And so I just wanted to give a cute example. So I grew up in Oklahoma, so we have a lot of prairie dogs. And so prairie dog burrows are a great example of using Bernoulli's equation to have a nice cooling effect. And this is something that human-made underground bunkers also do. So like military complexes, which is that if you have a more narrow, tall region, then we'll see in a moment that fluid tends to hug the ground. So it'll flow around this longer region, similar to a plane wing. And in that deflection, it'll pick up a larger velocity and therefore have a smaller pressure. Whereas if you have lower down, smoother openings, those will have a larger pressure, relatively larger pressure. And so air will flow from the high pressure region to the low pressure region, which ventilates the little prairie dog burrow. And so humans picked up on this idea and also use it for their underground establishments. Like during the Vietnam War, this was a really common technique because of the importance of underground bunkers for the Viet Cong. So they would use methods like this. You could hide entrances in trees and things in order to have increased airflow that leads to proper ventilation. So it's a really handy trick. Okay, but now we should hop on over to viscous fluid flow. So this is section 9.7 in the book. And the idea is that we know from experience that not all fluids flow the same, right? There are thicker fluids, like honey, for example. And then there are thinner fluids, so things like water or even air. And we can attach a number to this idea with viscosity, which again, fluid flow uses a lot of Greek letters, right? So we saw gamma with surface tension, and now we have eta, which I'm going to draw in an exaggerated way here. So it's like an N, but you give it a fun tail. So this is the Greek letter eta, if you're trying to look things up. And so eta is our viscosity, and it's given in units of pressure times time. And we'll see why that is in a moment. But basically, the bigger eta is, the more viscous a fluid is. And you can see a couple of relationships here. So one relationship is that these like fattier or more like high concentration solution based fluids tend to have higher viscosities. And that's just because there's more material in there, more interactions, more opportunity for the fluid to behave in this kind of thick way. And you can also notice from this chart, because they give some temperatures, that at higher temperature, viscosity decreases. So the reason for this is actually really straightforward. If you increase the temperature, you're making the molecules move faster. And so they're not interacting with each other as strongly as if they were allowed to sit still and get close to one another. So if they're sitting still, they get close to one another, the interactions are strong, the viscosity is high. But as we heat things up, for example, motor oil in cars is a really interesting example, because if you've ever changed your oil, you'll notice that it's really thick when you pour it in there. But as the car heats up, which is where the lubrication from the oil becomes important, the viscosity dramatically decreases. So the viscosity of actual hot flowing oil in a car is super low, and it can easily flow, just as easily as water. You can see how those numbers are very comparable. Whereas when it's cold and you're pouring it in, it's like 100 times more viscous. So it's a dramatic effect. And this is, anyways, there's I could go on a whole aside about this. I also want you to notice that, the adage that's been jumbled, over history and now means like the opposite of what it originally meant, that blood is thicker than water, is quantitatively true in terms of viscosity. So blood is about 3 or 4 times more viscous than water. And this temperature relationship makes that a little less apparent, but you can even see comparing to the 37-degree blood with the 20-degree water, that it's even still more viscous, even though the blood is a higher temperature. So with viscous flow, we get a couple of complications, and they lead to a really interesting result that's incredibly important for medicine, and is basically why people die from plaque arteries so easily. So this will explain why restricting blood flow even a little bit is a very dangerous thing. And so this originates with this diagram where for an ideal fluid, every particle of the fluid, if you have a constant diameter pipe, they'll all be flowing at the same speed. Okay, there's nothing from what we were just doing with Bernoulli's equation that says anything about how close are you to the pipe exterior. But with viscous fluid flow, the fluid on the walls, you can think of it as if it has more friction, it's interacting more. And so that fluid tends to be slow moving. And in some approximation, you even can take it to be stationary, that there's a coating of fluid on the walls of the pipe that just doesn't move at all. That's not quite true, but it's a pretty good approximation for simulating these things. And then the flow towards the center is faster. And so this is something that you'll notice, even though water isn't very viscous, if it's flowing through a rocky environment, it exhibits similar behavior. And so with rivers, if you've ever like floated down a river, I don't know if that's a very common pastime here. It was where I grew up, but you'll notice that the water in the center of the river flows a lot faster. And so if you're wanting to hurry back home, you want to get your little tube in the center of the river. But if you're just kind of lollygagging, you can stay on closer to the bank and you'll move slower. But anyways, so the drag forces involved here are a little complex, but what I want to point out is that, the change in pressure across the pipe, so from the center to the outside, pressure is just a force per area. And so we could ask ourselves, what is the force that's causing this pressure? And what is the area over which this pressure is acting? Okay, so the force causing the pressure is the drag force. So that's coming from this thickness, the friction, the viscosity of the fluid as it flows through the tube. It's dragging on the sides. That's causing this fluid on the sides to slow down and causing this difference in pressure. So that's why we want to use the drag force in the numerator here. And then the area is just the cross section of the pipe. So that's the area relevant for where this pressure can actually exert a force. So if it pushes on the sides of the pipe, nothing happens. As long as the pipe is strong enough, it'll contain the fluid. But if it pushes down the pipe with this pi r squared, that cross section, it'll move the fluid. Okay, so that's where we're interested in the difference in pressure. And so we can plug these things in. This equation, you don't actually need to know. So we can just take this whole thing for granted once we've worked through it. But this is the drag due to a viscous fluid. And you can see, like we mentioned last week, or sorry, earlier this week, and a little bit in 3a, that it depends on v to the first power. So this drag force is, remember, it was like b times v. Well, now we get to see all the things that go into that constant. There's a viscosity, there's an 8, and there's a length of the tube. So those are all the relevant quantities. Okay, but then what we want to do with this is we want to get some fluid flow for a viscous fluid. So fluid flow for a viscous fluid. And I always forget this guy's name, so I'm just going to look it up really quickly. This will give us sorry. Wissous equation, so some very French man. And basically what we want to do here is we want to take this, so we have this delta P, which is from the drag force over the cross-sectional area of the pipe, is 8 eta VL over R squared. We can solve this for V. And we get delta P times R squared over 8 eta L. And then remember that this flow rate is just V times A. So we can plug in this velocity, and then our A is again just pi r squared. And so we get pi r to the 4th times delta P over 8 eta L. And this is our Puiseux's equation, however you'd like to say that. And I should have mentioned this. So there was a pi here, and you may have wondered where it went. It turns out the drag force just also has a pi in it, and so they cancel. So if you're wondering where that pi went, it just cancels with the drag force. So we only get one factor of pi, but the crazy thing about this equation is that we get the radius to the 4th power. Okay, so what that means is that if I have a blood vessel or an artery that blood is flowing through, and I make it half as big, I cut the radius in half by, maybe it got pinched, or maybe there's plaque fatty buildup in the blood, in the artery. If I cut it in half, the flow rate is 1/16 as big. Isn't that crazy? So it's a very dramatic effect. R to the 4th is incredibly strong dependence. So even a small change in the radius of a pipe for a viscous fluid, which blood reasonably viscous, not terribly so, but decently viscous. Even a small change in the radius results in a really large change in the flow rate. Okay, so watch out for this. It's an important phenomenon, even if it's named after someone whose name is hard to pronounce. Okay, and then I won't say too much about this, but as we mentioned with the prairie dog burrow, air tends to also exhibit friction with the ground. So some viscous flow relative to the ground. And so we can talk about what's known as boundary flow and the corresponding boundary height, which is this delta Y boundary. And what this is telling you is basically that the closer you are to the ground, the slower air is going to be traveling. And so pilots make use of this sometimes in order to fly more easily. You can get closer to the ground and you get this boundary effect. But basically the height where you get to 90% full speed, so this, so the air up here is going 90% of its speed if there was no ground at all. That height from the ground to that point is this boundary height, Y boundary. And so I don't anticipate asking you too many questions about this, but you might just be expected to plug into the formula some sort of problem like this. And so if you know how long of a stretch of ground the wind is blowing over, that's your X. Your eta is the viscosity of the fluid. So air has some viscosity, even though it's very, very small. And the rho is the density of the fluid. So you can see that a less dense fluid actually makes this boundary height larger, which is the only reason we can see this effect in air. It has a very low viscosity, which would tend to make this height very small. So that would tell you that there wasn't much friction with the ground, except for the fact that air has a very low density. So that causes it to actually shoot back up. And then times in the denominator times the normal free velocity. So what it would be if there were no ground. And so putting this all together, you might just be asked to plug into these, this sort of equation. It would be given to you. Don't worry about it too much. But it's an important effect when you're thinking about weather patterns. So this is part of the reason that, when a hurricane, for example, makes landfall, you'll see it moving really fast in the ocean, and then it'll dramatically slow down as it moves up, the land. That's due to this boundary effect. So that height delta Y is large enough that it can exert a drag force on a whole hurricane and slow it down as it travels. And that will cause it to quickly lose its rotation, which makes it dissipate, which is why you don't have to worry about hurricanes very much if you're situated far away from the coast. Okay, and so this is where we get in back to talking about laminar versus viscous flow. And so this is the way that we can tell what kind of flow we're going to have. And so it's with this object known as the Reynolds number. So the Reynolds number, like it says here, is a balance between inertial forces and viscous forces. And the book is weird. It actually talks about this in chapter 5. So if you want to review this material, you have to go back to chapter 5. I don't know why they put it there, but anyways. And so the inertial forces, that's basically a way of saying how much mass does some system have, how much tendency does it have to continue at a constant velocity. And so that's coming from the velocity and from the density, and then from the length of either an opening in a pipe or an object that it's flowing around, some relevant length for that fluid flow problem, right? If you just have fluid flowing through an infinite box, then there's no Reynolds number. You just can't talk about a Reynolds number at all. But in reality, fluid's always flowing relative to something. If it's weather, maybe that's relative to the size of a valley. If it's blood in your arteries, maybe that's relative to the diameter of your arteries. So there's always some length scale for real fluid problems, and that's what the L is going to be in the Reynolds number. And then the eta in the denominator is related to the viscous forces. That's just your viscosity. And so this calculation that I have for you here, this is the Reynolds number for a salmon. And so you can see that for a salmon and a normal adult salmon, so we have the density of water, we have a typical velocity for a slowly moving salmon, and then we have a typical size for a salmon, around 15 centimeters. And then eta here is the viscosity of water at some cool temperature, so room temperature. And we get a relatively large number. And so what you should know is that if you get a large number, then we can model the drag as being proportional to v squared. So for a large Reynolds number, we want to use this equation, this v squared equation. You don't need to know the details of these coefficients. Basically, you just need to know that this is sort of some number times v squared, and this is some number times v. And these are the drag forces. Okay, so for a high Reynolds number like that salmon, we can think of the drag as being quadratic, whereas for a low Reynolds number, we think of the drag as being linear. And this also, so the reason for the difference in the drag formulas in these two situations is because the Reynolds number is telling us about how turbulent the flow is. Okay, I don't know. Yeah, I make a note of that here. So for a fluid that's flowing nicely, smoothly through a pipe or around an obstacle, we call that laminar flow. And so through a pipe, the criterion is that if the Reynolds number is less than 2000, then that would be laminar flow. And if it's around an object, if it's less than 1, that would be laminar flow. Whereas turbulent flow occurs for these larger Reynolds numbers. So over 4000 through a pipe, you're going to have the fluid flowing really choppily, right? Moving in all different directions. So that's turbulent flow. And that's why we want to use this v squared, this quadratic drag formula, right? So when the fluid is flowing nice and smoothly, we can tell that that's happening by the fact that the Reynolds number is small. Then it's not bumping into each other as much. There's not as much drag force. And that's why it only depends on velocity to the first power. Okay, so when the fluid is flowing smoothly, the velocity dependence of the drag is smaller, just v to the first. When the fluid's bumping around and jostling and doing all this crazy stuff, which we can tell is happening by a large Reynolds number, then we say that the drag goes like v squared. So that means that as we change our velocity in this turbulent flow situation, the drag force changes faster. If we double our velocity when it's turbulent, then we quadruple our drag force. And that's because turbulence creates these little wakes, these little eddies and swirls and things And those take up energy. They steal your energy into this rotational motion. And so the drag force increases more dramatically with higher velocity in those cases. So this is something that I want you all to learn. So there will be problems about it eventually. It won't be on the quiz tomorrow. I can tell you that much at least, but I'll probably give you some homework or something on this. And yeah, anyways, we'll pick this up next or tomorrow, but I just wanted to add that viscous flow, it turns out, is how we measure blood pressure. So I don't know how many of you all have measured blood pressure before, but we'll talk about that tomorrow.